Grignard reagents, or Grignard reactions. They use Grignard reagents. Okay. So remember that these will take place between these carbonyl-containing compounds and these MGBR businesses here, which we call Grignard reagents. Okay. We have two sort of carbonyl-containing compounds that are pretty similar, aldehydes and ketones. Which one are we looking at here? Aldehyde, right? When it's on the very end, it's an aldehyde. If it was, for example, picked up and moved over here in the middle of a molecule, that would be a ketone. Either one will react with the Grignard. In this case, we have an aldehyde. Okay? And before we kind of get going, the goal is going to be to predict the products, but just to kind of take this step by step and think about it, let's first take a minute and try to identify which carbon in my aldehyde is going to have my new bond, right? We're going to be forming a new bond between these two reagents, between these two reactants. Which carbon in my aldehyde is going to have that new bond? Everybody take a second. All right, we got a special name for that carbon, actually, because of the type of bond it's in. All right, so we're going to be making a new bond between our carbonyl carbon. All right, and which carbon in our Grignard is going to have this new bond? 1, 2, 2, right? The one that's attached to that magnesium. All right, so now let's see if we can't remember. Everybody take a second and see if you can't predict the products of this reaction here. Again, you're going to be connecting these two carbons. Okay, so what I'm going to do is I'm going to start. I need all these carbons in my product, right? All the carbons from the aldehyde and the Grignard reagent need to make it into my product. So I'm going to start by drawing these 1, 2, 3, 4 carbons here. Okay. I'm going to keep this color-coded. This was my green one here. All right, I'll get to this oxygen here in a second, but let's just finish out drawing our carbons here. All right, how many more carbons do I need to draw? 2, right? The 2 from my Grignard. 1, 2. When I draw my new bond, as we said, on the other side of that, needs to be that blue carbon, right? Because that's how these two molecules are being connected. So then I have one more to go here. Boom. Okay? So just looking at the carbon backbone, let's make sure that we can convince ourselves that our 1, 2, 3, 4 carbons from our aldehyde and our 1, 2 carbons from our Grignard have made their way into the product, and I've connected those 2 carbons that we were talking about, right? The green and the blue. The last thing we got to remember is this oxygen doesn't go anywhere, but it does not stay a carbonyl group. What's the new functional group in my product? An alcohol, right? So oxygen is still attached to this green carbon here, but instead of being a carbonyl, it is going to be an alcohol group. So this is my product of our Grignard reactions. Taking an aldehyde or ketone reacting it with the Grignard and creating an alcohol. Again, the pain in the butt about these reactions is if you take it step by step, make sure to pay attention to who you're linking up. The process-wise, it isn't so bad, but we do get these big, ugly products on the other side. So just trying to look at it and figure out what's going on is much more difficult. You kind of got to go through the process when you're building these products. All right, so before we move on, let's just practice that. We got a not so bad case and then kind of like a worst case scenario here. Bless you.
So the order that they are doesn't matter?
Nope. I specifically switched them up just so we can get used to it. I have a tendency to like default to a certain pattern, but it does not have to be like that, right? I mean, it's kind of like A plus B is the same thing as B plus A. All right, so again, I want to identify which carbon in my, in this case, ketone, and which carbon in my Grignard are going to be connected. I'm going to start by drawing these ones here, 1, 2, 3. All right, I'm going to keep that green one kind of colored so we can make sure to connect there. You can put the alcohol group on now, you can wait till the end, doesn't really matter, okay? But importantly, when I draw my new bond, on the other end of that needs to be that blue carbon, right? That's what I've identified is going to be linked together in this reaction. So then in order to finish this off, I need to make sure to include the 1, 2, both carbons. Do it in a normal color. Boom. Okay. So again, let's just make sure, again, counting carbons, let's make sure that we can see how these 1, 2, 3 carbons from my ketone are now connected to these 1, 2 carbons from my Grignard. All right, now look, in an ideal world, when we draw a carbon with 4 bonds, we draw it as a cross. All right, but for the sake of if it helps your brain seeing what's going on, if you want to draw it like this because it's just a little bit easier to see how you get from one side to the other, I'll allow it, all right? Again, you will see me and you will see textbooks. Anytime carbon has 4 bonds, you always draw it with those 90-degree angles. If it makes it easier to see how things are being linked up here, I'm fine with that, all right? Finding these products is already hard enough, all right? So we can leave it like that. All right, so here, again, same idea. We're going to find out what two need to be linked. To keep my colors similar, I'm going to do carbon at the base of my magnesium. All right, that's going to be linked to my carbonyl carbon in my product. All right. Start with my pentagon again. This would be my green carbon. Okay, remember that now needs to have that alcohol group. So I'm going to get that sticking off on one side. And then that new carbon-carbon bond. So on the other end of that is my blue carbon. All right, but now my Grignard's this big ugly thing. Again, that's kind of the beauty of the Grignard reagents is that it can be anything on the other side here, and this reaction works wonderfully, right? So it could be something as tiny as an ethyl group, or it could be this big ugly ring. It could be whatever you want, right? And of course, the bigger it is, the uglier your product's going to be. So I got to make sure to attach. Whoops, I somehow got rid of my blue. I got 1 and then 2, so let's put that on there. Okay, because then this thing's going to have this whole ring attached to it here, right? And how can we double check our product, especially when it's big and ugly like this, to make sure? Count them. Just go through and count them. It's so easy to accidentally put an extra one in here or forget one. So just go through at the end and tap a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Perfect, great. All right, but sort of just to zoom out to see our examples here, and I will keep my color coding the same. Okay, but again, these are these Grignard reactions. These are what we introduced on Monday. Okay. Our next reaction that we're going to learn about is another organometallic reaction. So it's going to also involve a metal. This is what's called a Gilman reagent, or Gilman reaction, using a Gilman reagent. All right, and what we're going to see is we're going to have an alkyl halide, so something with a halogen on there. And our what's called a Gilman reagent. Does it always flash like that? It's driving me nuts. God. Stop. Okay. Our Gilman reagent. So again, organometallic. The metal here is this copper lithium combo. Okay. Just like before, just like our Grignard reagent, it's attached to some big carbon group, some big organometallic group. All right, the weird thing here and what you're going to see is that when you build your Gilman reagent, it's actually going to bind two of those groups to it, but only one of them ever gets used in the reaction. Drive me nuts. Okay, so what we're going to do is we're going to have a sort of substitution reaction here where we replace our halogen with this R group. So our product of these reactions, and again, it's only, even though there's two of them on here, only one of them gets used in the reaction. It's going to contain our 2 carbons from our alkyl halide. We're going to form a new bond with the carbon at the base of that halogen. And what's being stuck on here is an R group, in this case, because I just left it generic R. All right, so this is kind of our generic formula for these Gilman reactions. An alkyl halide plus a Gilman reagent. You do a substitution and replace that halogen with that R group, whatever it may be. All right, so let's do, we'll start sort of with the simple one here. I'm going to use a different alkyl halide. Remember, we got our various halogens that we can use here, so iodine, bromine, chlorine, the usual suspects, not fluorine for whatever reason. Okay, and then let's take a look at a specific Gilman reagent. Okay, and again, what's going to make these tricky is that we're forming new carbon-carbon bonds. So our product is going to be bigger and uglier than what we started with. So again, we're going to go through the same process. We're going to make sure to identify which carbon in our alkyl halide has the new bond. All right, again, it's the one at the base of the halogen. So this one here. All right, and then which carbon in our Gilman reagent gets our new bond, and it's again at the one at the base of the metal, this one here. Okay, so I'm going to start by drawing my 2 carbons from my alkyl halide. I'll keep that one colored green. I'm now going to draw my new carbon-carbon bond. So on the other side of this is necessarily that blue carbon, because those are the 2 that I'm linking together here. And then I'm done. What's the problem? I don't have the same number of carbons, right? Like a simple counting carbons would let you know that this isn't quite done yet. What I have forgot is this one, the one that's on the other side of my Gilman reagent, right? So I need to include that as well. Boom. My 4 carbon product here. All right, and so just to be sure, just to go through and color again, these 2 carbons are these, and these blue carbons here are what's on the other side. Okay, so we'll keep that example up there, and then let's just practice this a whole bunch.
reason as to why the parentheses is going?
So really what it's showing is, if we just go back here, when you build a Gilman reagent, you have to have twice as much of this R group in there than will actually be used in the reaction. It's just kind of how it sticks to the copper. You stick 2 of them on there, and then when you do your reaction, only 1 of them gets used up. But so that it's just kind of the magic of how this reagent works is you have to put 2 of them on there, 1 of them get used. So that's what the parentheses is showing you, is that there's 2 of those R groups on there. So that's just the convention for drawing a Gilman. All right, so again, once you've done it a few times, it might be able to shortcut it a little bit, but especially when you're starting, make sure to just go through the process. We're going to identify which 2 carbons I'm going to link together, right? We're creating a new carbon-carbon bond. So in the case of a Gilman reaction, it's the carbon at the base of my halogen and the carbon at the base of my metal, my copper. I'll start by drawing one of these 2, it really doesn't matter, but I'll do my green side here. So 1, 2, 3 carbons, right? These 3 here. 1, 2, 3, 1, 2, 3. And then it's that middle carbon that I've highlighted in green here. Okay, so now I need to draw my new carbon-carbon bonds. In this case, unlike the previous reaction where that oxygen kind of hung around and became a different functional group, now we're just totally nixing this chlorine, right? It's not going to appear in my product at all. So I'm just going to draw my new carbon-carbon bonds. On the other side of that is that blue carbon. So then in order to finish this off, I just need to draw those 1, 2, 3, well, I guess the 2 extra carbons that were attached to that blue carbon. So 1, 2, boom. Okay, and we can count carbons, 1, 2, 3, 1, 2, 3. So in my product, I should have these 6. What's up?
Oh, we didn't knock it off. We did it wrong.
Say it again, sorry?
We did it backwards. Like we did it down instead of up.
No, 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 no. You could take this thing and rotate it 360 degrees and it'd be the exact same molecule, right? Rotate it 1 degree, whatever. You could, any sort of way that you rotate this, exact same. All right. right, so then our next one here, just a little bit bigger and uglier because we got a few more carbons. All right, again, process is the same. I'm going to identify which two carbons I'm linking. This one here, and the one attached to my copper. I'll start by drawing one of these. Let's do these 1, 2, 3, 4 carbons from my alkyl halide. All right, and again, I'm going to keep that green one colored because that's the one that has my new bond. So now I'm going to draw that new bond, and again, on the other side is the blue carbon. So now I need to make sure to include what was attached to that blue carbon. These 1, 2, 3. Okay, but it's in that little fork. So 1, 2, 3. Boom. All right, and I can go back and count carbons. Again, I got 4 from my alkyl halide, 1, 2, 3, 4. And I also have 1, 2, 3, 4 from my Gilman. What's up?
As long as you got the carbons, it's going to be right. So it doesn't matter how it's like structured, as long as the carbons are in there, like the right amount.
Yeah, I mean, so correct. In terms of like the orientation that you draw it in, that doesn't matter as long as I can go in there and count carbons. What's important, both the number of carbons, but also that they're linked together correctly, right? It's necessarily this carbon at the base of the halogen that's linked together with this carbon at the base of the copper, right? So as long as your linkage is incorrect and you have all those carbons there, the orientation on the page is not what matters. All right, so there's one more special consideration that we have to make with our Gilman reagents. All right, and this is that these reactions are stereospecific. But honestly, in terms of all the complicated stereochemistry crap that we've learned, this one's not bad at all. Okay? Let's say that we take an alkene that's attached to our alkyl halide here. And we react this with a Gilman. Let's just do a simple one here, small one. Remember this double bond here, unlike our alkanes, which can rotate about all those single bonds, this thing's stuck in this particular configuration, where the iodine's on one side and the methyl group is on the other side, right? This would be the trans configuration of this particular alkene, right? Pointed in different directions. So now when we're doing our reaction, first we got to do the same thing we did before, right? We got to make sure to link these correctly. So it's going to be the carbon at the base of my halogen, the carbon at the base of my copper. All right, but in theory I could get two different configurations here. I could get my trans product, where that new bond is linked on the opposite side, just like it was in my original reactant, right? My green carbon and my blue carbon. Or I could get the reverse stereochemistry, where I still have the same number of carbons in both of these, right? I've still linked those same two carbons together. But now these are different molecules, right? Because again, cis and trans, they can't interconvert. They're stuck because of the rigidity of that double bond. So I could get a trans product, or my stereochemistry could be flipped and I get the cis product, right? In theory, I could get either of these two. Okay? Now, in terms of a Gilman reaction, it's kind of best case scenario. Nothing complicated happens. We preserve our stereochemistry. So I'm not going to get this reverse stereochemistry here. My product will be the same as what it was above. Okay, so kind of best case scenario, you just link it on the same side as that halogen appeared in the first place. There are reactions that will actually switch the stereochemistry, or you'll get a mixture of products or something like that. This is a stereo-specific reaction where you only get this one product, and your new alkyl group from your Gilman is linked on the same side as your halogen. Okay, so because this methyl group and this iodine were pointing in opposite directions in my on my reactant side, they're going to be pointed in opposite direction on my product side as well. We're going to preserve our stereochemistry in these reactions.
Are we missing a carbon on that
So let's count.
the Gilman reagent?
So we got, on the green side, we got 1, 2, 3. And on the Gilman side, we only got 1, 2.
Oh, okay.
1, 2, boom. All right, so let's do some examples of this. So, same game as before, we need to figure out which two carbons we're linking together. Right, the one at the base of my halogen and the one at the base of my metal, my copper in this case. Start by drawing my 1, 2, 3, 4 carbons from my alkyl halide. All right, I'm going to make sure to put that double bond in. That's not going anywhere. All right, I'm attaching to this green carbon here. Okay. But importantly, because my halogen was pointed up, I'm going to preserve my stereochemistry and draw my new carbon-carbon bond pointing up as well. All right, that's the whole idea, is that it preserves the stereochemistry for these alkenes. So that's my new carbon-carbon bond. So I got to include the other 1, 2 on there, coming off like a fork. Boom, boom. All right, if we look at our alkene, the carbon on this side and the bromine were pointed on the same side of that double bond. So when I form my new bond, they're also going to be pointed on the same side, the cis configuration in both. All right, so then down here, again, let's identify which carbons we're linking together. This one here. And this one here. We're going to start with our, what do we got? 1, 2, 3, 4, and then a 5th one up there. And then keep my double bond. Oops. Here. All right, but then when I draw my new bond, so this is my, well, for real quick, this is my new carbon with my new bond here. So when I draw my new bond, am I going to draw it up here or over here?
Down there.
Down there, right? Because that's the direction that my halogen was pointed as well. So once I draw that new bond, I know on the other side of that is that blue carbon. All right, and so I can finish that off with the remaining 2 carbons that need to be attached on there. So I have a total of 1, 2, 3 from that Gilman reagent. Okay? Cool. So these are these 2 organometallic reactions that we learn about. They're kind of weird that they're put in this ethers chapter, but that's because really in a lab, ether's most common role to play is as a solvent. And these are 2 reactions that take place in ethers as a solvent. You see the ether's not doing anything. Everything's just floating around in that ether, right? But yeah, that's really the more common role to see ethers. And we will learn about some reactions of ethers, but really just like how to create them. All right, we'll go ahead and save that for next time though. Okay, so we can be done here with these 2. We won't start a new sort of set of reactions with, a few minutes left to go here. All right, so we're just going to pick up with the remainder of this chapter on Friday. All right, and again, I'll carve out some time at the end of class on Friday for you to view your exams.